In mathematics, a multivalued function is a left-total relation in which at least one input is associated with multiple outputs. In the strict sense, a well-defined function associates one, and only one, output to any particular input. The term multivalued function is, therefore, a misnomer because functions are single-valued. Multivalued functions often arise as inverses of functions that are not injective. Such functions do not have an inverse function, but they do have an inverse relation. The multivalued function corresponds to this inverse relation. Examples: every real number greater than 0 has two real square roots. The square roots of 4 are in the set +2, -2. The square root of 0 is 0. Each complex number except 0 has two square roots, 3 cube roots, and in general n nth roots. The nth root of 0 is 0. The complex logarithm function is multiple-valued. The values assumed by for real numbers and are for all integers. Inverse trigonometric functions are multiple-valued because trigonometric functions are periodic. We have, as a consequence, arctan is intuitively related to several values: pi, 4, 5 pi, 4, -3 pi, 4, and so on. We can treat arctan as a single-valued function by restricting the domain of tan x to pi 2 less than x less than pi 2, a domain over which tan x is monotonically increasing. Thus, the range of arctan becomes pi 2 less than y less than pi 2. These values from a restricted domain are called principal values. The indefinite integral can be considered as a multivalued function. The indefinite integral of a function is the set of functions whose derivative is that function. The constant of integration follows from the fact that the derivative of a constant function is 0. These are all examples of multivalued functions that come about from non-injective functions. Since the original functions do not preserve all the information of their inputs, they are not reversible. Often, the restriction of a multivalued function is a partial inverse of the original function. Multivalued functions of a complex variable have branch points. For example, for the nth root and logarithm functions, 0 is a branch point. For the arctangent function, the imaginary units I and -I are branch points. Using the branch points, these functions may be redefined to be single-valued functions by restricting the range. A suitable interval may be found through use of a branch cut, a kind of curve that connects pairs of branch points, thus reducing the multi-layered Riemann surface of the function to a single layer. As in the case with real functions, the restricted range may be called principal branch of the function. Set-valued analysis. Set-valued analysis is the study of sets in the spirit of mathematical analysis and general topology. Instead of considering collections of only points, set-valued analysis considers collections of sets. If a collection of sets is endowed with a topology, or inherits an appropriate topology from an underlying topological space, then the convergence of sets can be studied. Much of set-valued analysis arose through the study of mathematical economics and optimal control. Partly as a generalization of convex analysis, the term variational analysis is used by authors such as R. T. Rockefeller and Roger Wetz, John Borvine and Adrian Lewis, and Boris Mordukovich. In optimization theory, the convergence of approximating subdifferentials to a subdifferential is important in understanding necessary or sufficient conditions for any minimizing point. There exist set-valued extensions of the following concepts from point-valued analysis: continuity, differentiation, integration, implicit function theorem, contraction mappings, measure theory, fixed-point theorems, optimization, and topological degree theory. Equations are generalized to inclusions. Types of multivalued functions. One can differentiate many continuity concepts, primarily closed graph property and upper and lower hemi-continuity. There exist also various definitions for measurability of multifunction. History. The practice of allowing function in mathematics to mean also multivalued function dropped out of usage at some point in the first half of the 20th century. Some evolution can be seen in different editions of A Course of Pure Mathematics by G. H. Hardy, for example. It probably persisted longest in the theory of special functions, for its occasional convenience. The theory of multivalued functions was fairly systematically developed for the first time in Claude Berger's topological spaces. Applications. Multifunctions arise in optimal control theory, especially differential inclusions and related subjects as game theory, where the Kakutani fixed-point theorem for multifunctions has been applied to prove existence of Nash equilibria. This, among many other properties, loosely associated with approximability of upper hemi-continuous multifunctions via continuous functions, explains why upper hemi-continuity is more preferred than lower hemi-continuity. Nevertheless, lower hemi-continuous multifunctions usually possess continuous selections as stated in the Michael selection theorem, which provides another characterization of paracompact spaces. Other selection theorems, like Bressan-Colombo directional continuous selection, Kuratowski and Rilnardzewski measurable selection theorem, Aumann measurable selection, Frystkowski selection for decomposable maps are important in optimal control and the theory of differential inclusions. In physics, multivalued functions play an increasingly important role. They form the mathematical basis for Dirac's magnetic monopoles, for the theory of defects in crystals and the resulting plasticity of materials, for vortices in superfluids and superconductors, and for phase transitions in these systems, for instance melting and quark confinement. They are the origin of gauge field structures in many branches of physics. Contrast with bijection, injection, surjection,